So we've learned this new law, the universal law of gravitation, as seen through the Newtonian lens. We didn't get a chance to practice any questions, so before I send you on your way doing some practice questions for yourselves, I thought it would be only fair to run through a couple of sample calculations to show you what we're to try to get a sense of this law of gravity and why I was mentioning that it's the weakest force of the four fundamental forces that we talked about the other day. So basically, the way we look at it is we say that any two objects with mass separated by some distance will have this mutually attractive force we call gravity, that they'll each pull on the other. And again, Newton's third law says that if two objects interact, even through gravity, even over a distance, if one object is pulling on the other object with this force of gravity, then the second object is pulling back on the first object with exactly the same force. It's just the opposite direction. So when we get use that FG equation that we sort of derived today, all we're determining is the magnitude of that force. The direction of the forces depends on where these two objects are in relation to each other. So what we know is, if we were to look at this using sort of a grasp method, the information that we're given is that I've got the mass of one student is going to be 60 kilograms. The second student is going to be 80 kilograms. And the separation distance is going to be 1.4 meters. And what we're asked to find out is what's the force of gravity, the attractive force of gravity between these two, the mutually attractive force. So if we look at our analysis, we're using this equation, this Fg equals m1 m2 over r squared. So our g is the value that we have up here is 6.67 times 10 to the power of minus 11, and that's Newton meters squared per kilogram squared. I'm going to multiply that by the first mass, which is 60 kilograms. I'm going to multiply that by the second mass, which is 80 kilograms. It doesn't really matter which one I deem the first mass and which one is the second mass. The main thing is it's the product of the two, so it doesn't matter if I multiply 2 times 3 or 3 times 2 or 80 times 60 or 60 times 80. I'll still get the same product. So I'm going to divide this all by the square of that distance separating, which is 1.4 meters. So it's going to be 1.4 meters all squared. Let me add some space here. And I end up with a force, a mutually attractive force of 1.63 times 10 to the power of minus 7 newtons. And just to put this in perspective, this is 1.63 with 6 zeros before this and a decimal place. So 163 following 6 zeros and a decimal place. Or we say this would be 0.163 micronewtons, or millionths of a newton. And again, to sort of picture this in perspective, if you were to take a 1 kilogram mass, I'm just going to, if we put this in perspective, if I were to support a 1 kilogram mass, it's going to have a force of gravity that we said, based on that other calculation, is the mass. If that 1 kilogram mass were to be in free fall, it would accelerate at that 9.8 meters per second squared. If I were to just counteract that, just hold it in place. So if I apply a force over here, this would be 1 kilogram times 9.8 meters per second squared. I'd get 9.8 newtons. It would be acting downward. In order for me to hold this to have a net force of 0, this one would have to be 9.8 newtons up there. So just again, sort of picture a 1 kilogram mass. It's not that heavy, and you're holding it, and that's you're using about 10 newtons. This force, the attractive force, this is what I mean by how weak it is. This is like less than a tenth of a millionth of of a factor of that force that you would have to apply to a 1 kilogram mass just to hold it above the Earth. So to sort of get that sense of perspective, we've got two reasonably sized people, a 60 kilogram person, an 80 kilogram person, not very far away, and yet we've still got this tremendously weak force when you compare it to that perspective. And of course, we always end up with our therefore statement. So let's move on to part B of this question. So I'll look at this new situation. We've still got the same student is 60 kilograms. So we're going to have our first mass is 60 kilograms. Now we've got this near a blue whale. A blue whale is 130 metric tons. A metric ton is just 1,000 kilograms. So this would be 130,000 kilograms. So this would be M2 would be 130 metric tons, so or 130,000 kilograms. So it would be 1.3 times 10 to the power of 5 kilograms would be the mass of the blue whale. The separation distance here is going to be 10 meters. And again, so this is the information that we're given. We're being asked to determine what that force of gravity is between these two masses. And we do our math. Again, we'll substitute in our values to our G, M1, M2 over R squared. So 6.67 times 10 to the power of minus 11 Newton meters squared per kilogram squared. I'm going to multiply that by 60 kilograms again. I'm going to multiply that again by 1.3 times 10 to the power of 5 kilograms. I'm going to divide that by 10 meters all squared, and I end up with an attractive force of 5.20 times 10 to the power of minus 6 newtons. So even though we've gone to a whale, and I don't think you'd want to get much closer than 10 meters to a whale, just for your own safety. So we're looking at this massive creature with the same student is only going to increase that force at this distance by a factor of 10. So it's 10 times stronger, but it's still over 1 million times weaker than the force that it would take to hold up that 1 kilogram mass in our for comparison. So this is the upshot of this is that when we look at this, and by this is our substitute and solve, we're looking at this force of gravity between a blue whale and that same student. And of course, we end every solution with our therefore statement. The force of gravity between the student and the whale is 5.20 micronewtons. And so we'll complete these other ones. So here's part C. We're talking about the Great Pyramid of Egypt as with an estimated mass of 5.22 times 10 to the power of 9 kilograms. So we're talking a very massive object. Now it's about a kilometer away because we'd be looking at it maybe from that distance to sort of see, to take in the scope of the pyramid, to see it in its sort of grandeur. So we'll go through, I took the liberty of writing these things down ahead of time in the interest of time. So we got 60 kilograms for our first mass, 5.22 times 10 to the power of 9 kilograms for our second mass. The separation distance is 1 kilometer. So that's 1 times 10 to the power of 3 because kilometers is 10 to the power of 3 meters. And then we can just sort of plug and play. So now I've got 6.67 times 10 to the power of minus 11 Newton meters squared per kilogram squared. I'm going to multiply that by 60 kilograms and again by 5.22 times 10 to the power of 9 kilograms I'll divide that by 1 times 10 to the power of 3 meters, but all squared. So this will be 1.0 times 10 to the power of 3 meters. I'll square all of that. And I get 2.09 times 10 to the power of minus 5 newtons. So again, about 10 times stronger than the last one, but still it's ridiculously small. Like about, now we're talking about on the order of a fifth of a millionth of the force that it would take to hold up that 1 kilogram mass. This is our substitute and solve, and then our paraphrase. And there we have the force of gravity between the pyramid and student is now 20.9 micronewtons. And lastly, to look at a slightly more extreme situation, extremely small, let's look at the attraction between a 45-gram golf ball and that same student, and now they're separated by a little less than a meter, 95 centimeters. So we've got the mass 1 is 60 kilograms. The second mass is 45 grams, but we've got to remember our SI unit is in kilograms, so we have to convert that to kilograms. So I know that a kilogram is 10 to the power of 3 grams, so I'll divide it by 10 to the power of 3 or multiply by 10 to the power of minus 3 in kilograms to get that back to grams. And last but not least, the separation distance, so that 95 centimeters is 95 times 10 to the power of 2 minus 2 meters. Notice that I don't necessarily have to put these in scientific notation. The reason I do these is because, one, all I have to worry about is the conversion between grams and kilograms or centimeters and meters. If I can remember those, I can do these, and I don't have to worry about where do I shift the decimal place and whatnot. Your calculator will take care of that for you. All you have to do is remember that there are 100 centimeters in a meter, so I have to divide by 100 or multiply by 10 to the power of minus 2 from that 95. Then it's just a plug and play. Oh, and by the way, you can, if you're typing this into your calculator, that 45 would be EXP or EE, depending on your calculator, -3. And 95 EXP -2 for the separation distance. Now we just move over to the analysis and then the substitute and solve. We're going to substitute again the G 6.67 times 10 to the power of minus 11, 60 kilograms times 45 times 10 to the power of minus 3, all those numbers, and then we end up getting an attractive force of 2.00 times 10 to the power of minus 10 newtons. So that's about a fifth of a billionth of a newton. So ridiculously small. And of course, it would make sense. We don't get any sense of this attractive force between the 45-gram golf ball and the 60-kilogram student because it's so small compared to our everyday experiences of forces, that like that 1 kilogram mass that I'm holding up, that 10 newtons is like it's infinitesimally small, and this is why we don't see it on an everyday basis. This is the genius of somebody like Newton, who brings together the planets and the force of gravity acting on an apple.